Good afternoon, everyone. Sorry about that. We're fixing some problems related to the audio of the videos. I apologize if the videos you watched before had some issues, and it should be solved now. Okay. Let's see. The last thing we discussed was about 1D or one-dimensional mechanical Earth models, which basically take into account the heterogeneity of the subsurface in terms of mechanical properties in order to build a profile of horizontal stress. And if you remember, these are the equations that we used. And they, as a function of the Shear Modulus and the Poisson ratio, and as a function of tectonic strains, epsilon 11 and epsilon 22, they tell you what are the horizontal stresses at a given location. And later, we further extended that concept when you have a variation of Shear Modulus and Poisson ratio as a function of depth, which in this case will be the axis number 3. In this case, when you have Shear moduli Poisson ratios that are different, and you have a given tectonic strain, your stresses are also going to be different. The stiffer the rock, the higher the stress. Yes, Jack.
The previous one, when we assume that string 1, 1 and string 2, 2 is not equal to 0, and we assume sigma 3, 3 is
this is the case. This is the case. Epsilon 1, 1 is not equal to 0. Epsilon 2, 2 is not equal to 0. Yes?
And we assume sigma 3, 3 is vertical surface stress. Are we assuming the box regime is reverse path?
No? No, because those can be significantly small so that the horizontal stresses are still lower than the vertical stress. So probably at this point, and thank you for that question, Jack, because we could talk about what you have to do in the project. So in the project, I gave you a log file with VP and VS as a function of depth. With that VP and VS, you have to calculate the dynamic Shear modulus, dynamic Poisson ratio, and multiply that times the factor conversion from static to dynamic, that's SD, and so that you get the static coefficients. And with that, you're going to use these equations to tell you how stresses vary as a function of depth. So let me show you an example, which is simpler than the one that you have in your notes, but it's similar. All right, so if you go to my undergrad notes, and let's see where that is. Calculation of horizontal stress according to linear elasticity. This is the point. And here you will see a step-by-step derivation of the equations. But I have here a Python file that makes a sort of an animation of these stresses as a function of the tectonic strain. Okay, so let's just, this is going to take some time. Just give me 10 seconds, and then we'll continue talking about that. Did you guys start working on that project? Yes? Number 3? No? I already gave you number 4. Do you all have copies of number 4? Yes? I also uploaded it in Canvas, okay? So probably number 4 is not going to be due this Friday, by the next Friday, so don't worry, okay? But that's going to take some time to develop the theory, and also some time to solve it. Probably, I think from previous experience, that was the most difficult one from all of the projects. Number 4, yes. What? It should be fine. It should be fine with 2 weeks. Don't worry.
No, because we have not covered everything on here.
I'll help you. I'll help you. Don't worry. Okay. So, okay, this is the animation that I have in. They are online. So here we have vertical stress. We have pore pressure. These are total stresses as a function of depth. And notice that now my Poisson ratio is equal to 0. Because the Poisson ratio is equal to 0, the horizontal stresses, S11 and S22, are equal to the pore pressure, which is not real. It's not real. That's not going to happen anywhere. Because everywhere we're going to have some Poisson ratio, let's say equal to, this is small Poisson ratio, 0.18. And now you see that your horizontal stresses are a little bit to the left to the pore pressure. Let me zoom in. And now we have an effective stress, which is the difference between horizontal stress and pore pressure. And we have a large effective vertical stress. With no tectonic strains, as we have right now, the effective horizontal stress is a fraction of the effective vertical stress and depends solely on the Poisson ratio. Let me increase the Poisson ratio a little bit more. Let's go to, let's say, 0.25. That's a typical value for a Poisson ratio. And that gives you that the effective horizontal stress is 1/3 of the effective vertical stress. Let's now start adding tectonic strains. So I'm going to add a tectonic strain direction number 1. And you see how now S11 starting to increase. Still, it is lower than the vertical stress, but now it's higher than the other horizontal stress. If I keep on adding tectonic forces in direction 1, there might be some point at which the horizontal stress in direction 1 gets larger than the vertical stress. So in this condition right now, what kind of stress regime do I have? A strike slip, right? Horizontal, vertical, horizontal. And if I were in a place in which I have tectonic strains which are significant in both directions, both of the horizontal stresses could be above the vertical stress. And in this case, we'll be in reverse. But still, I can have cases in which the tectonic strains are not 0, and they are still lower than the vertical stress. All right, there is one more variable there, and that variable illustrates the concept of effective stress. It's very important you remember that all these equations of elasticity are relating effective stresses to strains, are not relating total stresses to strains. Because if you do that, you'll get something wrong. You always have to relate strains to effective stresses. Effective stresses are the ones that really make the rock deform or fail. Total stresses will not do that. So in this last parameter, I have a parameter which is a pore pressure curvature, which if I change it, I'm going to be increasing the pore pressure. And notice that I didn't change the other parameters, but what stays constant here is the ratio between vertical stress and horizontal stress. The larger the pore pressure, the smaller effective stress gets. Total stresses are going to be similar. For vertical stress, it's going to be exactly the same. But what the equations of elasticity are going to give us is effective stresses as a function of strains.
So why is Young modulus not cooked with this model?
It is. So here you have Young modulus. So in this case, it's 1 million psi. For example, if I had a stiffer rock, remember this plot, okay? I can take also a let's see, and I'm going to change it. I'm going to say that now I have a Young modulus of 1.5. I run it again. Okay, well, I erased all the things I had. But you can modify here. And the larger the Young modulus, the larger the stress you're going to have in horizontal direction. But you do have a horizontal stress. These equations are the same ones that we wrote a little bit before, where EPS, it's a plane strain modulus. All right, so you have to do this for your problem, but you're going to have a Young modulus and a Poisson ratio at every single depth. And with the same equations that we used, you just apply it to every single point. And if you have the Young modulus, if you have the Poisson ratio, I'm giving you the value of tectonic strains. You know what is the vertical effective stress at each point. You can calculate those stresses. And the result is going to be a variable effective stress and total stress as well as a function of depth. So that's the ideal plot, and your plot is going to look something like this. Okay, we have to go a little bit further down. Yes, 7 point here. It's going to look something like this, which at every single depth you have a calculation of the horizontal stress value. Okay, well, let me tell you now why this is important. And this refers also to the last question of the project. We want to know these profiles of horizontal stress because there are going to be places where horizontal stress is going to be a local minimum. And if the horizontal stress is a local minimum, that means that, for example, at this particular location, if you start the hydraulic fracture at this place, the hydraulic fracture is going to be contained at this point because it's going to preferably open the rock in places where stress is the lowest, not only in the direction of the minimum principal stress, looking for the optimal orientation, something we already discussed, but also in terms of depth, looking for spots where also stress is going to be the lowest. So in terms of a more ideal model, we are going to be looking for something like this. If let's say that I have several layers of rock, and in those layers of rock, the horizontal stress is the minimum principal stress, and this one varies like this. If you were to start a hydraulic fracture somewhere over here, it will quickly go into this local minima. If you were to start it somewhere over here, it will tend to propagate, probably first open up in this layer that has a little bit of a less stress, and then as you continue increasing the pressure in here, it's going to propagate down, and after it will just start growing out of the plane in this direction. And it's only going to go into adjacent layers whenever the net pressure inside the fracture is enough to overcome this difference in stress. Don't worry about the things I just said, net pressure, all of that. We're going to see that later on in detail. But for now, the important thing about this project is to know that we can use elastic models in order to predict what is this variation of stress as a function of depth, and that's going to localize the hydraulic fractures. In your assignment, again, you're going to have something a little bit more realistic like this, but still you're going to have some local minima that, depending on where you place your perforations, that's going to dictate where the hydraulic fracture is going to stay. Yes, Bethany?
So I guess for the project, if we get a range, is the local minimum the lowest value within that range of depth?
Yes. And in the project, I believe I'm telling you where the perforations are going to be made, and I ask you to tell me more or less where the fracture is going to go, where it's going in between which depths it is going to stay. Okay? Okay, so what we have seen so far then, it's the construction of these one-dimensional mechanical earth models, and something we didn't talk much about, I told you that we will discuss more today, it's about this parameter. In the project, I'm just giving you a value, but I think it's important that we talk a little bit more about it, because it's an important parameter, and we need to know where it comes from. Okay, so let me write the equation here again. This coefficient is going to take care of this conversion from dynamic to static. The dynamic is usually measured with wave propagation, and the static is usually measured in triaxial tests, and also is the one that applies to the field. And they are not the same. Usually, or almost all the times, the dynamic coefficient is higher than the static coefficient. So let me change this. If I were to plot static Young modulus versus dynamic Young modulus, and if I had a line that was 1-to-1, usually you will find that for a given faces of a rock, you will have some variations, but these points are always going to be in a trend which is lower than 1-1. And this is where we get our parameter FSD. So if this is equal to 1, this is our parameter FSD, where FSD is going to be less than 1. For typical rocks, it's 0.4, 0.6, 0.8. It really depends on the type of rock. Usually, stiffer rocks that have less plastic strain, less irrecoverable strain, would have a higher number of conversion of static to dynamic. And the reason for this factor to be different, it's due to two causes. And instead of the Young modulus, let me talk about this in terms of the shear modulus. If I were to plot here, yes, the shear modulus of a particular rock, and here I were to plot the shear strain, what I would tend to see is that the larger the strain, the lower that shear modulus is. I'm using here shear modulus because the Young modulus is a modulus that incorporates what's inside in the rock because it's a volumetric deformation. And in order to get rid of the problem of fluids, let's just talk now about shear modulus. Usually in waves, we have a very small shear strain. Strains in the order of 10 to the minus 6. But sometimes when we do a perforation for a wellbore or a hydraulic fracture, these deformations tend to be a lot larger, 10 to the minus 3 or 10 to the minus 2. And you can notice that's 1,000 times bigger. And with those larger strains, you get some of these materials to undergo irrecoverable deformation that ends up lowering the value of the shear modulus. For example, also you may get some grain crushing, some propagation of microfractures that you do not have with wave propagation. So that's one of the reasons why the shear modulus tends to be lower than at large strains, tends to be lower than at small strains. Very small strain, high modulus, large strain, lower modulus.
Can you repeat the applications when you have large shear strains?
Here,
Yeah.
when you go to the field, for example, if you're drilling a wellbore, if you're doing a hydraulic fracture, if you're trying to explain processes in geological time scale, you could even have larger deformations, percents, and even more. Sometimes in geological time scale, you really see rocks bend like they were a piece of a polymer, and that's because they have been bent in a very long time. And the equivalent shear modulus or the stiffness modulus of the same material tends to be a lot lower with larger strain and with larger times. And that's the second parameter here. So one is the magnitude of the strain, and the other one is going to be the velocity of the loading. So here I'm going to plot the shear modulus as a function of this gamma with the dot means shear strain rate. So if I have a very high strain rate, like for example in a wave, if this is very small, 1 over that value is going to be something very high, right? And therefore, the G is going to be high as well. Okay, wait. Let me think that again. So very large shear strain rate, and this is going to tend to 0. Okay, it's good. Very large strain rate, this value tends to 0. And as it tends to 0, this is going to be somewhere over here, and this is going to be a similar trend. Again, this is where we're going to have elastic waves. When this value is very, very small, 1 over that value is going to be very big. And here we have geological processes. And somewhere here in between, we have engineering applications. And this problem is related to viscoelasticity. Something we didn't talk about it yet, but we'll talk a little bit later on. But just, to give you an example, like, that door that has a, how do you call that? How do you call that thing that amortiguates how you open the door? I always forget. It's mechanics is a dash pot, but in regular vocabulary, it's a what? A hinge? No, a hinge, no. What is on top? What's the name of that? I always forget. It's okay, I'll remember, okay? Yeah, that thing over there. If you try to open the door very slowly, it's not going to oppose a big force, right? It's just going to, you just can open it. But if you try to do it very quickly, then you will start activating what is inside, which is a fluid which is moving inside, and it's going to get stiffer, right? So it's the same thing with materials. If you try to deform them very quickly, they are going to be stiffer. If you try to deform them, giving them enough time to deform, they are going to be a lot softer. I'll remember the name of that. Yes?
For example, the strain rate for geometrical processes may be really small, right? But you're plotting here, it would be high, but it takes a lot of time to deform it geometrically.
Yes.
So I don't know, in my understanding, there would be a lower strain rate, right?
Yes. So a low strain rate, if this is very small, then 1 divided that value is going to be something very big.
Oh, okay.
That's why it's
okay.
it's in here.
It's reverse?
It's reverse. It's the inverse.
I'm sorry.
Yes. I'm sorry if this wasn't clear enough, but it's 1 over that number. I did this way in order to preserve these two shapes going the same way. So you could also, I'm not going to attempt to draw it, okay? But you could also think of this stiffness of the rock as a function of the strain rate and as a function of the shear strain rate. And this is going to be something like this, like a 3D surface, right? But usually, the larger the strain and the slower the process, the lower is going to be the equivalent stiffness of a material. You have a question, Rodrigo?
Yes. And this reasoning is worked for the shear modulus, but also to the bulk modulus and for the axial modulus?
Well, the thing is that when we get into the bulk modulus and into Young modulus or constraint modulus, you have one more variable that I don't want to get into that right now, which is the fluid inside. And it's going to be how much time it takes to the fluid to get out of the pores. And that's a different thing. It's not related to the mechanics of the rock itself from grain to grain contact, but it's related also to the fluid inside. So we're going to add that level of complexity later on. But that also adds some viscoelastic behavior that also results in these variations of shear modulus, or also bulk modulus as a function of the velocity of loading or the strain rate.
So this reasoning will be only applied for the S waves, for example?
Correct. For the S waves or for, in general, for the shear modulus or anything related to just the mechanics of the rock without taking into account the fluids inside. Yes. Okay. So, long story short, taking into account all these processes is routinely done, at least in petroleum engineering, through this correlation. And with this correlation, we are able to build these one-dimensional mechanical earth models. The model I gave you, it's an isotropic model, and it's relatively simple. Nowadays, for calculations and planning of hydraulic fracturing, when there are places that you don't know very well what's going on, you better go with something a little bit more accurate. And that's going to be a model that incorporates anisotropy. If you remember from a few lectures ago, we said that this is a matrix for isotropic media with just 2 parameters. And before that, we saw that there was another type of medium, which was the vertical transverse isotropic medium, where we have 5 independent coefficients. All right, so our goal now is going to be to build this 1D mechanical earth model with a vertical transverse isotropic medium. And before we do that, we need to know how to measure those 5 parameters, which is not as simple as just measuring Young modulus and a Poisson ratio. But that's where we're going to go. Okay? So let's get started. Remember that this is what we have in mind now. And let me see my notes here. I need to bring these from another set of notes. Okay. So let's see how we do this in the laboratory. All right, so let's imagine that we have a piece of rock, but now this is a rock with a clear lamination, in which, let's imagine, dark is soft and light is stiff. Here, we're going to add a coordinate system, and if I apply a vertical stress in direction 3, and I measure a vertical strain in direction 3, what am I going to get? In a test which is, you can say either these are the typical tests done for these measurements are done with constant confining pressure, but it could be similar to unconfined.
Quick question, is that a VTI or TVI?
It's the same. Sometimes I use TVI or VTI. It's the same thing. All right. So, and let's assume that this axis number 3 is the vertical axis. So, if you were to do such a test and get a sample in such orientation, if I apply stress in direction 3 and I measure strain in direction 3, the proportionality between these two is going to be the vertical Young modulus. Let's get a sample now in horizontal direction. I go to the coring room and now drill this rock in direction horizontal, and I get a horizontal sample. Okay, wait. There's a mistake here. I need to rotate my coordinate axis. So 3 is vertical. Remember, 3 is vertical. So 3 is going to be here. And if that's the case, 1 in this case is going to be there, and 2 is going to be there. So 3 is vertical, but in this case, I'm just putting the sample in vertical direction because we're going to load it axially. So you're checking the axes. Are they okay? 1, 2, 3. This is fine, right? Okay. So now I'm going to change stress. I'm going to load it axially in direction 1 and measure strain in direction 1, 2. What do I get now? The horizontal Young modulus. And if I were to measure the strains in the lateral direction here and there, in this case, for example, I could get the Poisson ratio 3:1, which is the expansion in direction 1 divided the shortening in direction 3. That would be the Poisson ratio 3:1. And that one, because of the symmetry of the problem, is going to be equal to the Poisson ratio in the plane 3:2. If I assume that this has a symmetry around the axis 3. And this is what we're going to call later on a horizontal Poisson ratio. Okay? Wait, no, I think this is the vertical. It doesn't matter, but what it matters is that what I'm going to write here, it's a different value. So I do the same test, and now I measure the expansion in direction 2 divided the shortening in direction 1, and this one gives me the Poisson ratio in the plane 1:2, which is going to be different than the one here. So notice that in the first case on the left, we are applying a stress in direction 3 and it's expanding in the other 2. And in this case, we're applying a stress in direction 1 and it's expanding in direction 2 and in direction 3. But it's not going to expand the same in the two directions here, in 2 and 3, because it's not symmetric with respect to the axis 1. So those are going to be different. But with all these measurements, I'm going to get 2 Young moduli and 2 Poisson ratio. Is that enough? No. Why? Because we need 5. We need 5, and for this particular case, there's no much more that we can do. So these tests with constant confining pressure or unconfined, these are usually done in a Tri-Axial cell, and it's also an axisymmetric Tri-Axial cell. And because of that, I cannot do anything else related to these conditions. Let me mention this one more time. in a triaxial cell, we haven't talked about triaxial tests, right? So let me tell you very quickly what goes on in a triaxial cell. In a triaxial cell, we have a cylindrical sample. I'm just going to do it 2D here, to which we apply stresses in one direction. Usually here, this is made of steel. This is a rock. But we apply stress in one direction, and we put a membrane around the rock so that I can apply pressure of the fluid, in this case called the confining fluid, into radial direction, sigma r, where sigma a is going to be equal or larger than sigma r. And in a typical deviatoric test, like the ones that are used for doing the test on the measurements that we were discussing above, this is done by making changes of the axial stress and keeping the radial stress as a constant. Okay. Yes.
That's the example on the right. You are still pushing in the direction 3, right?
Yes, with the, but I have in direction 1 and 2 and all around the sample, I have a constant confining pressure or a constant stress, sigma 1,1 and sigma 2,2. This symbol in math means that these are kept constant. And it's the same here, constant sigma 2,2, constant sigma 3,3. Probably, you know, here I can show you something. This is small triaxial cell that we use for doing triaxial tests in this setup. And inside this goes filled with fluid. And once we fill this with fluid, we connect these outlets to this pump, which is a syringe pump that keeps a constant pressure. And after we do that, we basically get a rock sample and put it in between these two steel cylinders. We put the rock in the middle, so that will go over there. And then we put a membrane, which goes covering the rock. So at the end, we have something like this. Like this. And applying fluid from the sides and applying stress from the top with a low frame allows us to do these measurements of deformation and also of strength. In this case, it's not, probably you cannot see how we measure strains on the sides, but this machine is not designed to do that. Downstairs, we have another one that allows you to measure strains on the sides. Okay, so we have solved one part of the problem, which is what we're going to call the coefficient Cij, but the static coefficients. Because we have done this using a triaxial cell with large deformations and relatively large, although sometimes they are not that large, or relatively small strain rates. It's not like the one of a wave. Okay, our objective now is going to be to measure this Cij, but with waves. Okay, I need to check that again. All right, so let's see how we do this now with waves. And this is going to be the dynamic part. So all of this was static. Let's do now the dynamic. All right, so for the dynamic one, again, we're going to get a sample drill vertical with respect to bedding. We have 1, 2, and 3. And now what I'm going to do is I'm going to use waves to measure the stiffness in different directions. So the first one I'm going to do is I'm going to send a P wave that goes in direction 3, 3. So this is going to be BP 3, 3. A P wave going in direction 3 is going to cause deformations also in direction 3. So which stiffness coefficient am I going to recover from this P wave? Let me bring the matrix so I can help you answering that question. Okay, we need to go all the way back over here. My question is, I'm causing perturbations only in epsilon 3, 3 with waves that with an actuator are applying variation of sigma 3, 3, and I cause epsilon 3, 3. Which is the proportionality parameter between sigma 3, 3 and epsilon 3, 3 when all the others are 0? See? C33. So if I measure this P wave velocity, this is going to give me directly C33. And C33 is going to be the density of the rock times BP33 squared. If you remember from what we saw from the isotropic media, stiffness coefficients were also a density times a velocity square. And in the transverse isotropic medium is the same, but now we have to be more careful with the directions that we use. Okay, I have one parameter. Let's send the wave in direction 1, 3, and it's a shear wave. And I'm going to call this one BS31. Is traveling in direction 3, is causing deformation in the plane 3, 1. Let me add this over here. This one is causing deformation epsilon 3, 3. This one is going to be causing deformation, strain deformation in the plane 3, 1. All right. Same thing. Which is the parameter that links epsilon 3, 1 and sigma 3, 1? C44. C44 is going to be the density times BS31 square. Okay. Not many laboratories have this, but we have it here at UT. You can also send a shear wave which is perpendicular to the previous one, and well, let's put 60. I don't think we're going to go 60 minutes again, but let's just put 60. I can send a shear wave perpendicular to that one, and that's going to be BS32, causing shear strain in the plane 3-2. And which proportionality coefficient should I get here? Also C44, right? So it's the same. We didn't get any new value. So this is as good as we can do for this particular example. And with P and shear wave velocity measurements from one end to the other, we just recovered C33 and C54. Okay, so let's go now to the next one. Now we are going to use a horizontal sample, and let's see, the coordinate system is 3 and 1 and 2, and we're going to send a P wave in direction 1 . Let me see if I can apply some colors here so this looks nicer. BP. All right. I'm not going to show you the matrix now, but I guess that you already know by now which parameter am I going to get with BP11. C11 and what parameter do I get with a shear wave in direction 1, 3. I should get C44, but I already had C44, so let me just skip that one. But the one which is very interesting, which we didn't have yet, it was this one, which is VS12. And VS12 is going to give us C66. C66 is going to be BS12 squared. And now we have 4 parameters. We're still missing one. And the way that we're going to measure that 5th one is by getting one more sample, but this one is going to be called with respect to bedding. What, Jack? It's this is called, this is a vertical sample, okay? This one is horizontal. This one is called 45 degrees. So if I send through here now a P wave, which I'm going to call BP45, and oh, wait, I need to add the axis here. So the axis is going to be something like this: 3, 1, 2. If I send a wave at 45 degrees, that's going to cause strains in direction 2 and in direction 3, and the result is going to be that I'm going to be able to measure the parameter C13, which is going to be a function of this BP45. It's a very long equation, so I don't want to write it, but I'll send you the paper where you can find it, okay? But the idea is that now using these 3 samples, you can actually measure the 5 parameters of the stiffness matrix and characterize this TVI medium. Lately, there have been some other developments in which instead of measuring the velocities just from end cap to end cap, sometimes you can use just one sample like this, and you can also put transducers here on the sides, and you put more transducers here on the top and on the bottom. So combining the transducers that go on the top and the ones that do ray paths that go at some angle, you can also retrieve some of these other coefficients that if you just have these transducers, piezoelectric transducer at top and bottom, you have to go to the 3 sample method. We're doing something of this now in my laboratory, using one sample and by using more sensors in order to tell you what is an anisotropy of the rock. And finally, after you have done all of this, the idea is to, same as we did before, to have a CIJ. By the way, all of these are CIJ dynamic. After you have all of these dynamic CIJ, wait, I always make the same mistake. After you measure the static CIJ, and after you measure the dynamic CIJ, be it C11, C33, C13, anything, is the same idea as what we had before, is to plot these values and obtain a correlation for each value CIJ. So now instead of just having one value, you may have 5 of these conversion values.
So do you mean plotting maybe 5 or 10 C13 values, or a combination of C13, C44?
No, you compare 1 to 1. You compare C11 static to C11 dynamic. But I'm just, instead of making 5 plots, I'm just making one here. Okay? But it's valid for all those.
How do you get those C13 to be static?
Very good question. So the static, you cannot get it, right? There's some people that claim there are some methods that you can get it. But what is usually done is to make, for example, a correlation between C13 and let's say C66 or C44, and use that correlation in order to tell what is going to be C13 as a function of the other. Actually, let me go a little bit more in detail. Once you get C11 and C66, C12, this is just an equation related to shear in the plane 1, 2. It's going to be C11 minus 2 times C66. So what you actually do is you make a plot of C13 as a function of C12. And let's say C13 is 1.2 times the value of C12 in the dynamic range. Well, then you use the same for the static. And thank you for that question, because I didn't clarify how to get from here to there, right? So these are stiffness coefficient, and these are Young moduli and Poisson ratio. So in order to get from Young moduli toCij's, you have to use some equations. And let's see if I have them here. I don't think I do, so I'm going to have to pull up that paper quickly. Okay. Not this one. Okay, I think this is the one. Let me try that. Yes. So PDF here. Okay. So here you have some examples of some nicely looking laminated shales. These are some of the things that we already discussed. And here you will find the equations that allow you to calculate those values. So this is what we just saw. And here you have the equation for C13 based on BP45. Okay? So you need before C44, you need C55. And then with that additional value of BP45, you can get C13. And in order to calculate the Cij from the vertical, the horizontal, Young moduli, and the Poisson ratios, you have to use these equations, which are a little bit complex, but they are just equations, okay? So you can do it. The equations were developed some time ago. We used it for some particular problem of tracking the nonlinearity of these values, how those Cij vary with stress and with confining pressure. All right, so, but you can have them, okay? There is a way to calculate what is the static Cij as a function of this Young moduli and Poisson ratio. Okay, so before we move on, I'd like to do one more exercise. Let me see if, yeah, I'd like to do that before we go into something else. Question, which is going to be larger? The horizontal Young modulus or the vertical Young modulus? So we have a rock here. Again, it is made up of layers of soft and stiff materials. And here I'm going to apply stress, measure strain, and the result is going to be a vertical Young modulus. And I'm going to have the same sample, well, not the same, but the same rock. And apply stress and measure the horizontal Young modulus. Which one is going to be higher? And I'm going to give you further details of this. The dark is going to be soft, and we're going to call it E soft. And the light is going to be E stiff. And the same thing here. All right, before doing any math, just trying to understand what's going here. What is going to be, which one is going to be larger? Which one? Horizontal. Why?
I only think about the marshmallow and metal example.
Okay.
If you think about it this way, because it is soft, it's going to compress a lot more.
Okay. Yes, I like the marshmallow example. I did it with Oreos, but it's the same with marshmallows, right? You could imagine the white stuff as marshmallows and the black as, well, no, let's do the opposite. The black as marshmallows, thin, and the white as cookies. So if you're just compressing the marshmallows, that's going to be a lot softer than doing this one. Okay, let's see the equations that are going to allow us to quantify that. Let me see if I find it. If I don't find it, I'm going to have to do them from scratch. Not here. Okay, here. All right. Let's go with the first case. The vertical Young modulus is actually going to be what is called a volume average of this entire thing. And these brackets are going to mean that. It's going to mean a volume average of the applied stress, which is going to be sigma v divided the total strain in direction, in vertical direction. The same way, I could say that the vertical strain is going to be proportional to the vertical stress, and it's going to be inversely proportional to this bulk modulus.
So if you add the bracket,
It means I'm thinking of this medium as a black box, and it's everything I measure as a total amount. So forget about what I have inside here. At the end of the day, I'm just going to measure some deformation. If I consider this a black box, that's going to be that strain. Okay. The change of length divided initial length. Okay? All right. So our objective is going to be to relate this vertical Young modulus to the moduli that go inside in the material. All right. So what we're going to do then is we're going to calculate what is this total strain. As we said, the strain is going to be equal to the total deformation, right? And the total deformation is going to be a summation of the deformation of the stiff part plus the deformation of the soft part, right? All right, so what is going to be the deformation of the stiff part? Notice that each of these layers is going to have the same stress. And each layer then is going to have a strain which is going to be sigma v divided, let's do the first stiff part, divided the Young modulus of the stiff part. That's going to give us the strain of the stiff layers, right? Now I'm going to multiply that times the length of the stiff layers, of all the stiff layers, okay? And I'm going to call that the summation of the length of all the stiff layers, L stiff. And now it's a displacement, right? Let me add to this now the strain in the soft layers, and okay, this looks okay. I'm going to multiply that, the length, total length of all the soft layers, the summation of all of that, and we'll divide all of these well, let me do it over here so it looks a little bit nicer. The total length, where the total length is going to be this. So I have displacement, divided total length, that should be strain, right? And if you know this from here, what is going to be the total length of the stiff region divided the total length? What? It's going to be a ratio, but it's just going to be the volume fraction of the stiff part. So this is going to be sigma v is stiff, L stiff divided LT. This is a volume fraction. It's a volume fraction of the stiff part, how much of the stiff layers you have. And the same as this one, the total length of the soft layers divided the total length is going to be the volume fraction of the soft components. And now, since this one is the same as that one, if I now compare this one to this one, I'm going to have that sigma v divided this is sigma v divided this and as you can see, the sigma v is everywhere, and I can take it out, and as a result, the Young modulus in vertical direction is going to be I always forget what is the name of this. This should be a geometric average, right? Do you guys remember arithmetic, geometric average? I don't know why, but I always forget which one is which. But this is the final equation. So if I know how much of the stiff section I have and how much of the soft section I have, and I know the individual Young moduli, I can calculate the vertical Young modulus. And I can do the same the horizontal one. Any question about the vertical? Something very important to notice here is that even if you have a small fraction of the soft part, because of the way this equation is written, that's going to have a lot of influence in the final Young modulus. I'm going to show that in an example. Okay, for the second example, it's a little bit more difficult because not all the layers have the same vertical stress. Actually, what happens, this is a model called isostress, and it's also called a Roy's average in geophysics. The model that we're going to see now is called isostrain, and this one is also called a Voigt average. All right, so in this case, it's a little bit more difficult. And I'm just going to do it 2D because 3D gets more complicated, but it's about the same. Let's say that we have this layer rock. We're going to apply a deformation in vertical direction so that all the layers get shortened the same direction. And it may expand also a little bit because of the Poisson ratio effect. But all the layers are going to get the same strain, okay? If all the layers get the same strain, and this is, the dark is softer than the light, what is the result? Is the stress going to be constant along the rock? It's the same case as the one that we had before with horizontal strains. Here, I'm going to have higher stress in the stiff layers, and in the dark layers, I'm going to have smaller stress. So the stress is not going to be a variable. What is going to be a variable is the stress is going to be a variable, and what is not going to be a variable is the strain. from this displacement, the horizontal strain is going to be equal to the average of all those horizontal stresses, but this is a weighted average because it depends on how much of each material you have, divided the equivalent horizontal stress. And that weighted average of horizontal stress is just going to be equal to the strain in each layer divided the strain times the Young modulus of each layer times the length of each of these layers. So now this is going to be LT, and each length of the layers is going to be L soft, is going to be the length in this direction of the soft layers, and the same with L stiff. Let me see, I'm forgetting something over here. So, no, I think I'm good. So total sigma h is going to be sigma h soft times the length of all the soft layers divided by LT plus sigma h stiff times the length of all the stiff layers divided the total length, and sigma h soft is just going to be, if you see from this equation, it just has to be EH times E soft and this one is going to be just EH times E stiff, and the total sigma h from this equation is just EH times the average horizontal modulus of the entire thing, and EH is everywhere, and the result is that the horizontal modulus is just an arithmetic average of the summation of the two moduli, L stiff divided LT, where again these two values are volumetric fractions. So the more soft material you have, the smaller is going to be EH, but it's a linear relationship. So let me tell you now why this is important and how these equations come into the picture. Let me find now this other paper. That shows that very clearly. And also shows it in an application for shales. I hope this is the paper. All right, this is what we were seeing. What you see in this figure is Young modulus in the y-axis as a function of amount of clay and kerogen for shales, where clay and kerogen are considered the soft part of the material. So the softer or the more clay and kerogen you have, the lower the Young modulus is going to be. That's why those two lines are decreasing. And the less clay and kerogen you have, the stiffer your rock is going to be. Okay? So, more softer material, then lower Young modulus. Let's now see the horizontal and vertical. The vertical values are, well, let's go first with the horizontal. Horizontal values are the inverted triangles, and you see that for the same type of rock, let's pick this Barnett, number 1. For the same type of rock, horizontal Young moduli tend to be larger than vertical Young moduli. Let's see, for this Haynesville rock, also horizontal Young modulus is larger than vertical Young modulus. And the same repeats for all the samples. And again, you can see the variation with the amount of the soft part. But also very important in this plot are these two lines. These two lines are the ones that we just derived. The first one was the isostress, the one that predicts the vertical Young modulus. And the important thing to remember out of here is that a very small quantity of the soft component is going to lower that vertical Young modulus a lot. As that quantity increases, it's still, you know, that vertical Young modulus is going to be low, but it's already quite low, even with a little bit. But it is not the same with the horizontal Young modulus. The horizontal Young modulus, even if you have, when you have a small quantity, still it's quite large. And of course, at the two end members, when you don't, when it's 100% stiff or 100% soft, they should be exactly the same values. And these are the two models that we just saw, trying to predict that stiffness in vertical and horizontal directions. So in general, rocks, sedimentary rocks, are going to have a Young modulus which tends to be larger in horizontal direction than in vertical direction, except one case. Can anyone tell me which case that's going to be? Sometimes, you were saying something?
It's on a graph.
What?
It's on a graph, right?
Yeah, no, but I'm telling you, there are going to be some cases in which the vertical modulus may be larger than the horizontal. It's not in the figure, but we discussed it some time ago. Sometimes we can have fractures in a medium which may create additional compliance in horizontal direction. If the rock is not fractured, horizontal Young modulus should be larger than vertical Young modulus. But if it is fractured, and especially with vertical fractures, at the larger scale, your horizontal Young modulus may be lower than your vertical Young modulus. Okay, so I think that was enough for today. There is just one more thing we have to do in order to finish this up, but well, we'll finish on Wednesday. We need to use now all these equations in order to predict horizontal stresses with horizontal and vertical Young moduli and horizontal and vertical Poisson ratio. But those are just a few equations. All right? Okay. I'll see you on Wednesday. And we didn't talk anything about project number 4, but we'll get to that on Wednesday. All right?